Hello and welcome to this lecture on fundamentals of electric drives. Now, in the last lecture we were discussing about half control converter fed separately excited DC motor. Today we will take up the discussion on 3-phase fully controlled converter fed separately excited DC motor. Now, we are talking about a 3-phase converter, and 3-phase converters are used for higher power application, typically higher than 10 kilowatt. So, when we have 3-phase, we have input a 3-phase AC supply. So, our topic today is 3-phase full controlled converter fed separately excited DC motor. Now, let us see the topology of the converter. The converter basically gets the supply from a 3-phase supply, and it is in the form of a bridge usually. So, we can sometimes call this to be a bridge converter. So, we have 6 SCRs and these are all SCRs. The input is supplied from a 3-phase AC supply. We have phase A, phase B and phase C. The output feeds the armature of the DC motor. So, we have resistance, inductance and back EMF. And the back EMF is E. So, this is the armature of the DC motor. Now, these SCRs can be named from 1 to 6, because we have 6 SCRs, we can number them from T1 to T6. So, we have T1, T2, T3, T4, T5, T6. So, the output current is IA and the output voltage here is armature voltage is VA. Now, we will confine ourselves only to continuous current operation, because in this case the discontinuous current only happens for a very narrow range of operation. So, we will only concentrate on continuous current operation, continuous conduction. Now, we have to draw the output voltage waveform, that is VA. Now, we can draw the output voltage waveform in the following way. This is how we can draw the output voltage waveform. In the x axis we have omega t. So, we have 3 different voltages VAB, VBC and VCA. These are the line voltages. So, we can plot the line voltages first. This is VAB, and we have VBC, and then we have VCA. So, this voltage is VAB. This voltage is shifted from VAB by 120, this is VBC. The third one is the AC input voltage, that is shifted from VBC by again by 120 or 2 pi by 3, this is VCA. We have to also draw the negative of these voltages, that is VBA, VCB and VAC. So, the reverse of this voltage, let us say VAB, this is we have here VBA, the reverse of this voltage, that is VAB. So, this is VBA. Reverse of BC is VCB. So, we have VCB which is like this. And then we have the reverse of VCA, that is VAC. So, VAC is here. This is VAC. Now, this can be very well understood if you draw the phasor diagram. If we draw these 6 voltages, we have the phase sequence is ABC here. This is VAB, this is VBC which is lagging this by 120 and VCA is here, and the negative of VAB is VBA, the negative of VBC is VCB, and the negative of VCA is VAC. Now, what we do here in case of a full control bridge, we delay the triggering angle. So, the triggering angles are delayed from the instant of crossover. Now, in this case, for say for example, during this region VAB is the maximum possible voltage VAB. So, from this instant to this instant VAB is maximum possible voltage. So, when we say VAB is maximum possible voltage, so the SCR T1 and SCR T6 are most forward biased. So, had there been diode, the output voltage would have been like this. Now, this would be the output voltage when we replace the SCRs by diode. So, this would be the natural output voltage if we have uncontrolled rectifier. It means the SCRs are replaced by diodes. For let us say between this region to this region, we have VAC is the most positive voltage. Similarly, from this region to this region, we have VBC and so on. So, these are the instant at which there is crossover between the two voltages, two line voltages, and one voltage becomes the most positive voltage, and that SCR pair will naturally be most forward biased. So, what we do here at this instant, we take our reference, and we delay the triggering angle by let us say some value that is alpha. So, when we delay our triggering angle, we have to vary the output voltage. So, this is called the triggering delay and this angle is called alpha. Now, when we delay the triggering angle, output voltage will be like this. This will be delayed actually. So, instead of following this violet color pattern, it will follow the green pattern. Similarly, from this instant we delay the triggering angle. So, the output voltage will look like this. So, VA is now look like this. So, this is the nature of VA. Similarly, for the other SCR also, we can delay the triggering angle. So, in that case the triggering angle is delayed. So, we get the output voltage which looks like this, and alpha in this case also can be varied from 0 to 180. So, this is the output voltage of a 3-phase bridge, full control bridge here. So, if we see the x axis, so this is the 0 here, and here we complete one half cycle pi, and then we complete one cycle, that is 2 pi, and these are the things where pi by 3 and this is 2 pi by 3 and so on. So, this is in the x axis we have the angles, that is omega t. Now, what we have to do here, we have to find out the average output voltage. The average output voltage can be found out by integrating over 1/6 of a cycle. Now, here we see the ripple frequency in one cycle here, that is from 0 to 2 pi, we have 6 times the SCRs are triggered. At this instance, what we do? We trigger SCR here at this instant, T1 and T6. At this instant, we trigger SCRs here, VAC is most maximum. So, this is T1 and T2, and at this instant VBC is the most positive voltage. So, in this case we trigger T3 and T2. So, this is T2 T3, and then at this instant we trigger the next pair. Here VBA is maximum. So, it is T3 T4, and at this instant VCA is maximum. So, we trigger T4 T5 and so on, and at this instant we have the maximum voltage here is VCB. So, CB means it is T5 and T6. So, this is how the SCRs are triggered. In complete one electrical cycle, we get 6f ripple. So, here the ripple frequency is 6f. So, the output ripple frequency of output voltage is equal to 6f, where f is the input supply frequency. Now, we have to find out the average output voltage. Now, when we find out the average output voltage, that is VA, what we have to do here? We have to integrate from, let us say, pi by 3 plus alpha. If we assume that VAB is our reference, so the angle starts from 0 here. So, this is our reference in this case. So, we integrate from pi by 3, because this angle is pi by 3 here. So, pi by 3, and we are delaying it by an angle alpha, and then this continues till 2 pi by 3 plus alpha, because every delay is alpha. So, this is 2 pi by 3 plus alpha. So, we are basically integrating over this region. So, our voltage here is Vm sin omega t, and we have to integrate over d omega t, and if you take the average is 1 by 2 pi by 6, because that is the 1/6 of a cycle, and 1/6 of a cycle means it is 2 pi by 6. Now, if we simplify this, what we get here? This is 3 Vm by pi. Now, this is sine. So, we have minus of cos. So, we get here cos of pi by 3 plus alpha minus cos of 2 pi by 3 plus alpha. So, if we simplify this one, we will finally get here the value, the voltage in this case as follows. So, the voltage V A is given by 3 V m by pi into cos alpha. So, this is the output average voltage. So, if you simplify this, we will get cos alpha. So, the output is 3 V m by pi cos alpha. Now, what is V m? V m is the peak of the line voltage. The input is AC. So, the line voltage. Now, that is equal to root 2 times V line or line to line voltage. So, we can also write this V A as 3 into root 2 V L L by pi into cos alpha. So, we are assuming that the current is continuous, because we have 6 step ripple, the possibility of the current coming down to 0 is remote. It only occurs at a very narrow range. So, we will not discuss the discontinuous current operation for this course. Now, here if we want to plot the speed torque characteristic, we have to equate this voltage to the armature drop and the back EMF as before. So, this is equal to IaRa, the DC machine, plus the back EMF. So, from this we can obtain the speed torque characteristic. Omega m is equal to 3 Vm by pi into cos alpha divided by k phi minus T R A by k phi whole square. Now, in this case, when we plot this speed torque characteristic, here the no load speed is given by this value. So, here the alpha can be variable, alpha is from 0 to 180. So, there is a possibility of this becoming negative as well. So, this is the torque speed characteristic for a fully controlled converter. Let us say alpha is equal to 0 here, alpha 30 degree, alpha 60 degree, maybe alpha 80 degree and so on, but for alpha is 90. So, this is for alpha 90 degree, assuming continuous current conduction, because when alpha is 90, the no load speed is equal to 0. So, this is, let us say, omega m in the y axis and torque in the x axis here. So, this is the torque speed characteristic of a 3-phase full control converter fed DC motor drive, and this is used for higher power application. When the power is large, instead of a single phase converter, we go for a 3-phase converter. Now, we will now discuss the multi-quadrant operation of DC drive. There is necessity that whenever we have a drive, we may have a single converter, which can be a full control single phase converter or full control 3-phase converter, but we would like to operate the drive in multiple quadrant. So, what are the various steps which will ensure that the drive can be operated in multiple quadrants? So, we will be discussing about multi-quadrant operation of separately excited DC motor. Now, let us say the first one is by using mechanical reversible switch in the armature. Now, what we have here is the following. We have a converter which is feeding the armature of a DC motor, separately excited DC motor. We have a 3-phase full control converter which is feeding the armature of a DC motor, but what we have here, we have a reversible switch. So, this is a converter which is feeding the armature, and these switches are represented by RS, a reversible switch here. Now, the current is flowing in this direction and we have the voltage. So, this reversible switch can be given in the following fashion. So, this is the armature. So, the reversible switch means we have 4 switches here, one pair of switch connects like this. This is called the forward switch, and other pair of switches will connect the armature in the other direction. So, if we say that this is our point A and point B, this point A is this point and point B is this point. So, we have 2 pair of switches, one is F A prime and we have R and R prime. Now, F and F prime are normally closed switch, they are normally closed switch. So, we can say NC switch, NC switch. So, normally we have a forward voltage applied here. So, this voltage is positive because A is connected to the output of the converter. So, the current flow is in one direction. Now, when we open this switch, this is a normally open switch. When we open this NC switch, NO switches will be closed. So, in that case the current through the armature will be reversed. So, the current through the armature will be reversed. So, for example, if we have A and A prime here, this point is A and this point is A prime. So, A prime is connected to A and A is connected to B if R and R prime are on. So, what we do here is the following. We go from step 1, step 1 is called forward motoring. So, if you want to reverse the quadrant, we go to step 2. So, step 2 is first is forward braking, we have to go for braking here, and then we go to the third one is the reverse motoring. Now, how can we go from step 1 to step 2 to step 3? Now, when the motor is running in the forward direction, if you want to reverse the motor, this cannot happen automatically by a single converter. So, we have to follow a few steps. So, first of all we have to brake it, that is called forward braking. So, how can we brake it? We first increase the triggering angle alpha. This bridge was operating at a triggering angle alpha. So, what we do here, we increase triggering angle alpha, advance alpha, so that the armature current IA comes to 0. This is step 1. So, what we do here, we advance the angle alpha here. So, if you advance this angle alpha, the voltage, the output voltage here in this case VO would be negative. So, in that case this this current will not be supported by the input voltage. So, I A will gradually decrease down to 0. So, when the I A decreases down to 0, what we do in that case, the field in this case is separately excited. We are not changing the field connection, the field is separately excited. Now, when this I A comes down to 0, we take the step here that reverse the armature connection, reverse the armature connection by the reversible switch, by the reversible switch. So, the armature connection is reversed by using this reversible switch, and then the third step, the armature connection is reversed, and then start alpha the braking at maximum value of alpha and gradually reduce alpha So, what we do here is alpha is started at a maximum possible value, and to break the motor at constant current. So, in this case the connection has reversed. So, the back EMF has reversed here. So, when the back EMF is reversed, we have to advance the triggering angle alpha. So, alpha is advanced here. So, this is how we have the armature in this case. So, the back EMF has reversed. So, we start at an advance alpha, but the current is always positive. The current is positive, but what happens to the torque? The torque in this case has reversed, because the armature connection has reversed. The torque in this case is given by minus k phi I A. Because the armature connection is reversed, we have a reversal of the constant. So, in this case T is equal to minus k I A. So, the torque becomes negative. When the torque becomes negative, the braking takes place. So, this is basically the braking, but what we have to do here, we have to control alpha to brake at constant current. So, the torque is negative. So, we are in the braking mode. So, I A is controlled to brake at maximum possible torque, and then gradually the speed is reversed. The motor speed reaches 0, speed reaches 0. So, this is basically the end of the forward braking, this is end of forward braking. Then since the armature connection reverse, torque is negative, the speed reverses, then the speed reverses. So, when the speed reverses, it continues to accelerate in the negative direction and runs in reverse motoring. This is called reverse motoring. So, we basically go from which quadrant to which quadrant? We have quadrant 1. So, from the first quadrant we go to the fourth quadrant. The fourth quadrant is braking. So, this is the speed and this is the torque here. So, we go to the second quadrant, and from second quadrant we go to the third quadrant. So, this is how we proceed from first quadrant to second quadrant, and then we break here at maximum possible value of torque, torque is reversed, and then we operate in the reverse motoring condition. So, from forward motoring, this is forward braking, and then we operate finally in the speed goes down to 0, but the torque is still negative because we have reversed the armature connection. So, here we operate in reverse motoring. So, this is how we can change from one quadrant to other quadrant for a separately excited fully controlled converter fed DC motor. Now, here what we do here, we use mechanical contactors to change the armature connection, which is sometimes not very convenient. So, instead of a mechanical contactor, we can do the same thing electronically by having a dual converter. So, we will be discussing about a dual converter, which consists of two converters connected in anti-parallel fashion, that will smoothly change the operation from forward motoring to forward braking to reverse motoring, and this we will take up in the next lecture.